Hello, Year 12. Today's lesson is going to be just an introduction to quantum physics. This unit is also called quantum physics. We're going to look at two models, the particle model and the wave model. So the first type of model that we're going to look at is particle models. So in order to explain the properties of matter, we often think about the particles of which it is made and the ways in which they behave. So we imagine particles as being objects that are hard, they have a mass and move about according to Newton's laws. When two particles collide, we can predict how they will move after collision based on what we know about their masses and their velocities before collision. Here we have a picture of a pool table and pool balls. They provide a very good model for behavior of particles on a much smaller scale. Particles are a macroscopic model. That basically means that they're larger scale models. So our ideas of particles come from what we observe on a macroscopic scale. For example, looking at the motion of the stars and the planets, working with trolleys and balls in a lab. We can also apply particle models to the microscopic world and explain more phenomena. So, for example, we can picture gas molecules as small, hard particles rushing around and bouncing haphazardly off each other and the walls of the container. We call this the kinetic model of gas. We can explain macroscopic phenomena of pressure and temperature in terms of masses and speeds of microscopic particles. This is a powerful model used to explain many other aspects of the behavior of gases. So here are some examples in this table of different particle models that we use in science. For example, in the area of electricity, we have a model of the flow of electrons, and the macroscopic phenomena is the current. The same with the area of gases. We have kinetic theory, which I've just touched on earlier, looking at the macroscopic phenomena of pressure, temperature, and volume of a gas. And then in solids, we have a model of crystalline materials, and the macroscopic phenomena are the mechanical properties. In radioactivity, which you would have done as well at GCSE, we have the nuclear model of the atom, and we have the macroscopic phenomena of radioactive decay, fission and fusion reactions. You can also look at the area of chemistry, where we have a model of the atomic structure, and the macroscopic phenomena are the chemical reactions. Now let's take a look at wave models. So when we think of waves, we think of them as something that we see on the oceans, tidal waves, or maybe just small ripples in a pond. For physicists, it's shaped, as in this diagram, like a sine graph. More complicated waves can be made up of several simple waves. We can use the principle of superposition of waves by adding up the displacements of the waves at each point. So waves are a way in which energy is transferred from one place to another. In any wave, something is changing in a regular way while energy is traveling along. In water waves, the surface of the water moves up and down periodically, and energy is transferred horizontally. And that's, of course, a transverse wave. Here we have some examples of different phenomena using the wave model in science. So, for example, sound. The varying quantity could be pressure or density. Light and other electromagnetic waves. The varying quantity could be the electric and magnetic field strengths. And another phenomena are waves on a string, and the varying quantity is the displacement. The characteristic properties of waves are that they all show reflection, they all show refraction, they all show diffraction, and interference. Waves themselves do not have mass or charge. Since particle models can also explain reflection and refraction, it is diffraction and interference that we regard as the defining characteristic properties of waves. If we can show diffraction and interference, then we know we are dealing with waves. So wave models and particle models are both useful, but they can explain many different observations. But which should we use in a particular situation? And what if both models work when we're trying to explain something? This is the problem that physicists struggled with for over a century, to be honest, with light. Does light travel as a wave or as particles? In the 17th century, there was a pretty big battle raging between two views about whether light traveled as waves or particles. And this battle raged between two gentlemen. One was called Huygens, and in 1670 he thought that light was made of waves. So he said every point on a wavefront is a point source on a secondary wave. So if you have waves coming along in this direction, shown here by the arrow, every single point on this wavefront is a source of light. They all have ripples, just like throwing stones at every single point in a pond. You throw a stone in a pond and every single point generates ripples, and all the ripples combine to produce a new wavefront. And that's how wavefronts progress, by having each point being the source of a secondary wave, as shown in this diagram. Then Newton, on the other hand, by about 1704, I think he published this in a book, he said that light travels as particles. He could use the particle model to prove both for reflection and refraction. He basically said that light was made of corpuscles or particles. He suggested that was the reason why when you fired light at a mirror, it would reflect or rebound. And he also proposed that light traveled faster in water than in air. Most people, until about 1853, agreed, rather than agreeing with Huygens, agreed with Newton, until Foucault in 1853 came along, did some actual experiments to see the speed of light in water and in air, and he found that light traveled more slowly in water than in air. So that put an end to Newton's idea being the more popular version of whether light traveled as waves or particles, and as he suggested, particles. So people started to lean on the idea that light traveled as waves. Now, let's just quickly consider light as particles. So we expect light to behave as waves, but it can also behave as particles. And we can show this by taking a Geiger counter next to a source of gamma radiation, and you hear those irregular series of clicks. That's the counter detecting gamma rays. But gamma rays are part of the electromagnetic spectrum. They belong to the same family of waves as visible light, radio waves and X-rays and so on. So here we have waves giving individual clicks which are essentially indistinguishable from the clicks given by alpha and beta particles. So we can conclude that gamma rays behave like particles. So we can show using this method that gamma rays behave like particles when they interact with the Geiger counter. The effect is most obvious with gamma rays, as they are at the most energetic end of the electromagnetic spectrum. It is harder to show the same effect for light. Now I'll just run through this diagram here just so that you're aware of how it all works. So basically any alpha, beta or gamma radiation can enter through a window made of a substance called mica. Okay, so there's radiation can enter through the mica glass. Inside is a low pressure gas like argon. This is also unreactive. Alpha, beta, and gamma are, as we know, ionizing radiation. Once they enter the tube, they can ionize argon gas. So we might get an argon atom that is being negatively charged if it's had an electron put onto it, or positively charged if it's had an electron removed from it, and then it's called an ion, of course. Let's say we create a negative argon ion due to this ionization event caused by the gamma radiation or beta radiation or alpha radiation. That negative ion will be repelled by the metal cathode at the outer part of the tubes you can see on the diagram and accelerated towards the anode, which causes a tiny pulse of current, and that is detected by the circuit and sent to the counter or the rate meter. Now, just looking back again at history, because for a long time Huygens was ruled out, and then Foucault came along in 1853, and everyone was quite certain then that light behaved as waves. But even before that, in about 1804, I think, Thomas Young, a British physicist, did an experiment called the double slit experiment, which we looked at in waves. And basically, waves were directed at a double slit, separated by a distance labeled on the diagram as d. This is the distance between slits. And he looked to see what he got on a screen some distance away. What he got was a fringe pattern, which is shown there on the right-hand side of the diagram. This fringe pattern consisted of light and dark spaces. An equation was derived, which is n lambda is equal to d sine theta, where n here is any integer number, and lambda is the wavelength of the light source. Theta, well, theta 1, for example, is the angle to the first fringe, and theta 2 would be the angle to the second fringe, and theta 3 and so on with the angle to the third and fourth fringes. You could have other fringes all the way along, and theta will be obviously different for the different fringes. Each point on the screen represents a light fringe. And Young said that this showed that light was capable of interference, as you only get fringes through interference, and only waves can interfere. So, yeah, Huygens was right after all. Light is made up of waves and not out of particles. But again, all of this changed in 1887 through the photoelectric effect. Threw everything on its head again, because we'll look at the photoelectric effect later, and that again showed that light traveled as particles. So we are now in the realms of 1853 onwards, and thanks to the work of Foucault, and also especially I think thanks to the work of Thomas Young, we are now firmly back in the court where we think that light can be treated as a wave. Okay, so it's a wave with this continuous wave pattern of oscillating electric and magnetic fields traveling in a direction. If we sent light through a small opening, this electromagnetic radiation would spread out and there would be diffraction. Or if you had some wave in a region and it lined up perfectly with some other electromagnetic wave, you'd get constructive interference. If it was out of phase, you'd get destructive interference. That's what waves do. Why shouldn't we call electromagnetic radiation a wave? By the late 1800s and early 1900s, physicists discovered something quite shocking, that light and all electromagnetic radiation can display particle-like behavior as well. So we're sort of back to Newton's earlier ideas. So they discovered that light and light particles can only deposit certain amounts of energy. We call this amount of energy discrete amounts of energy. There's a certain chunk of energy that light can deposit, okay, no less than that. So this is why we call it quantum mechanics or quantum physics, because quantum means a discrete jump. What do we call these particles of light? Well, we call them photons. Okay. We know now that light can behave like a particle and a wave. So light shows wave and particle-like characteristics. There's just nothing else that can do this. I mean, both behave as a wave and a particle. So it's quite hard to draw it all out. But the way that we have a visual image of a photon is with a little wave-like diagram and an arrow at the end. Okay, so that's how we represent a photon. So let's imagine that we had some detector, okay, that's able to measure the light energy that it receives from some source of light. If it was sensitive enough, you would either get no light energy, okay, which is represented by the horizontal line, or you'd get this little jump, okay, and then you'd get again no energy, and then you get another jump, which is where a photon has been absorbed, but you couldn't get anything in between. If the quantum jump was 3 units of energy, for argument's sake, okay, so each photon was carrying 3 units of energy, you could either absorb no units of energy whatsoever, or you could absorb all 3 units where you get these little jumps, or but you couldn't absorb 2 units or 1 unit or a half unit. It's basically 3 units or none. That's why it's quantum mechanics, this discrete behavior, with light depositing all its energy in a particle-like way, or nothing at all. So how much energy is this photon depositing? Well, there's a formula for that. The amount of energy in one photon is given by E is equal to H multiplied by F, and E is equal to the energy of the photon, which is in joules. H is a very, very important constant called Planck's constant, which has a value of 6.63 times 10 to the power minus 34 joules second. And frequency is, of course, measured in hertz. So this relationship tells you that the energy is proportional to the frequency. Hence, you might have come across this. We say that high frequency radiation means high energy photons. Okay, Planck is a very, very important person. He's the father of, or sometimes known as the father of quantum mechanics. He was the first person to figure out what the constant was and proposed that light could only deposit this energy in discrete amounts. So Max Planck is a very, very important person in all of this. The energy of these photons, as you can tell, are extremely small. I mean, there's not many numbers as small as Planck's constant. Let's look at another example of how we could apply this. Okay. So let's say that we had some violet light, and we want to know what is the energy of one photon for violet light. Now we know that the frequency of violet light photon is 7.5 times 10 to the power 14 hertz. Okay, and we know the equation E is equal to HF, so we can put that in, and we know the Max Planck's constant, which is 6.63 times 10 to the power minus 34. We multiply that by the frequency, and that gives us the energy of one violet photon, which is 5 times 10 to the power minus 19 joules. Now that is very, very hard to notice. It's hard to notice that this energy is coming in this discrete amount. At a macroscopic level, light appears to be continuous and smooth, but when you really go deep down into these powers, you can clearly see that it's not so smooth. There are these little steps, these little jumps. Okay. Now we have our E is equal to HF equation, But we also know from previous lessons that we have the wave equation, which is c is equal to f lambda, where c is the speed of light and lambda is the wavelength of that light and f is the frequency of that light. Okay, so using E is equal to hf and c is equal to f lambda, we can produce another equation, which is E is equal to hc over lambda. And just to be certain, E is the energy of the photon in joules. H again is Planck constant, which is 6.63 times 10 to the power minus 34 joules second. F is the frequency given in hertz. C is the speed of the electromagnetic radiation, which could be light as well. 3 times 10 to the power 8 meters per second. And lambda is the wavelength given in meters. Now, the photon model or for electromagnetic waves consists of three basic postulates. Okay, three important points for it to be effective. Electromagnetic waves consist of discrete, massless units called photons, so they don't have any mass. A photon travels in a vacuum at the speed of light. The second postulate is that each photon has energy E is equal to hf, where f is the frequency of the wave and h is Planck's constant. In other words, electromagnetic waves come in discrete chunks or quanta of energy. Okay, and the third important postulate is that the superposition of a sufficiently large number of photons has the characteristics of a continuous or smooth electromagnetic wave. Okay. Right, what I'd like you to do now is have a go at a couple of questions, question number 1 to 4. Okay, so you can pause the video here and all the best. How did you get on? I hope you managed okay. Here are the answers with all the workings out as well. Okay, so hopefully you didn't find it too difficult.